For years, men followed the wind, captured it in their sails, and let it carry them to far places and great adventures. But all the while, they dreamed great daring dreams that the wind could carry them still farther, to their skies themselves. It was a dream that had to come true. If man could only find the power needed to fly like the birds. In time, the answer came with the invention of the internal combustion engine. So man had finally found the power to conquer his new world of flight. At last, he could fly. But little did these first pilots dream that air would someday become more than a pathway, that it actually would become yet another source of power, the very power that would make modern aviation itself possible. Power. Power to operate modern instrumentation and other devices. Power produced by air that we today know as aviation pneumatic systems. The first time it's seen, pneumatics appears to be a strange sort of word, but basically all it refers to is a flow of air to produce vacuum, which is the pull or suction of air, or air pressure, that is the push of air. Simple really, but it is this air vacuum and pressure, pneumatics, which provide a constant and reliable source of energy to operate a number of instruments and other devices in aircraft. These mechanical devices for accurately monitoring flight direction and relative position of aircraft to ground became essential, as did a source of energy to operate these instruments. Early aviation designers took their answer to this problem from the very air in which the pilots flew. Air, a constant source of energy, infinitely available and readily obtained. All you had to do was scoop it in, hence creating the airflow to operate the needed instruments. Early systems amounted to little more than this. They began with a venturi, a funnel-like device which was mounted on the fuselage directly in the propeller slipstream. The air passed directly through this venturi, thus creating a suction of air in the tubing connected to the instrument panel. This suction of air, or vacuum, operated gyro instruments which measured aircraft attitude and direction. The attitude gyro instrument showed the plane's position relative to the ground. The directional gyro instrument showed the pilot his direction of flight. The basic principle was quite simple. The moving air spun a gyro inside the instrument. The spin gyro, in turn, produced an instrument reference. Here we see this suction illustrated. As air passes continuously through the venturi, it creates a suction of air in the tubing from the gyro instruments. Air entering the gyros, because of this suction, is first filtered to protect the instruments. The gauge simply measures and indicates to the pilot the amount of suction in this system. The basic principle remains unchanged to this day. In fact, up through World War II, the simple airflow system, obviously refined, was the basic technique for pneumatics. However, a major problem with the early venturi system was the fact that ice could form at altitude, clogging the venturi. This restriction in airflow caused instruments to inadequately function. So a new and better system had to be invented to permit flying in adverse conditions. Some mechanical means was required to produce the necessary airflow. Thus was the wet air pump and system introduced to aviation pneumatics. Mounted on the aircraft engine and powered by it, the air pump provided dependable airflow in any weather. Further advances logically centered on air pumps, which became the principal component of any pneumatic system. The first air pumps used engine oil for cooling and lubricating. Therefore, this was referred to as a wet system. Like the venturi system, the wet air pump system operated on the basis of air vacuum. However, unlike the exposed venturi, the airflow, now created by a pump, was totally contained within the aircraft. Cabin air was pulled through the instruments with a regulating valve controlling the proper amount of vacuum. Cooling and lubrication for the pump were provided by engine oil, which was drawn through the pump at the same time as the air. A mixture of oil and air was forced out of the pump, where it was diverted to an oil separator. Most of the oil went back to the engine, and the somewhat oily air went overboard. A bit cumbersome and somewhat messy, to be sure. But the wet pump still was a big step in the right direction for aviation, and many wet air systems are still in use today. Not only did the arrival of air pumps eliminate the problem of Venturi icing, it also provided enough extra airflow to conquer yet another icing problem. When flying during inclement weather, such as rain, sleet, or snow, ice would build up on the leading edges of the wings and tail, creating dangerously excessive weight. It also disturbed the aerodynamic flow, thus reducing control, or at the worst, even causing loss of control. To solve this problem, inflatable rubber boots were developed which could be attached to those surfaces vulnerable to icing. These boots drew the air for their operation from the ample flow created by the air pump. While inactive, the boots are deflated. When ice forms, the boots are inflated, thus cracking off the ice. Once the ice is removed, the boots are again deflated. Special valves operated by the pilot control this function. Designers soon saw more tasks to be performed by pneumatic systems. And all this was made possible by the wet air pump. However, along with these benefits, the wet system also presented numerous disadvantages. For example, the need for oil separators made the system complex and heavy. Oil used to lubricate the pump could in time work its way through the entire system and eventually contaminate the rubber boots and control valves. Additionally, the oily air dumped overboard streaked the fuselage or wings. Obviously, something still better was needed. The answer was the dry system, pioneered by Airborne and introduced in 1957. Like the wet air pump, the dry air pump also is mounted on the aircraft engine and is powered by it. From here, the differences are significant, for introduction of the dry air pump amounted to a unique breakthrough in aviation pneumatics design. This successful development of a self-lubricating dry air pump now eliminated the need for oil cooling and oil lubricating. The dry system thus offered all the advantages of the Venturi and wet systems, but overcame the major disadvantages of both. The simple, lightweight, and dependable dry air pump is the heart of today's dry pneumatic systems. Clean, dry air does all the work in this system, eliminating the need for heavy oil separators and excessive oil lines. There is no oil contamination of the de-ice system, and the dry air system is easy to maintain. Yes, the dry air pneumatic system was a milestone advance for aviation. It opened the way for many more tasks to be performed by pneumatic power, tasks to meet important needs in aviation. Almost every year was bringing with it new demands for aircraft to fly higher, farther, faster. At the same time, pilots and their passengers were calling for greater safety, more comfort and convenience. And this led to increasing demands for performance from pneumatic systems, as well as adding to a growing list of tasks to be performed. For example, in addition to powering instruments and de-ice systems, pneumatic systems today must seal doors for pressurized aircraft. And they must energize autopilots. In addition, manufacturers, owners, and operators of aircraft were demanding longer life, greater reliability, and economy from their pneumatic systems. These performance demands called for basic and significant improvements in aircraft pneumatic systems. The dry air pump provided the basis for greater efficiency. Further improvements were made throughout the dry air system itself, to the point where this system is now nearly universal in the general aviation industry. You'll now find dry air systems in aircraft of many different types and sizes, largely because the dry air pump can deliver reliable pneumatic power through both of the two basic ways, vacuum and pressure. For a vacuum system, air lines are connected to the dry air pump's inlet port, which pulls air. For a pressure system, lines are connected to the outlet port, which pushes air. In a vacuum system, the air pump draws or pulls air from the aircraft cabin, drawing the air through the pneumatic system and those instruments attached to the system. In the pressure system, the air pump draws outside air through an inlet filter and then forces or pushes the air through the system and the attached instruments. Typically, the simpler and less expensive vacuum system is used on smaller aircraft, those with modest instrumentation and which fly at lower altitudes. Here are specific examples of aircraft which use vacuum pneumatic systems. Pressure systems are used on many larger, sophisticated aircraft which operate at higher altitudes. Aircraft such as these use pressure pneumatic systems. While vacuum systems perform well in the applications for which they are intended, they may be less efficient for high-altitude, high-performance aircraft. Here's why. A pump in a vacuum system operates with higher air compression ratios. This produces more heat in the pump. The thin, dry air found at higher altitudes lacks natural cooling capacity to offset this heat. At lower altitudes, the heavier, more moist air found there has the natural cooling properties to counteract heat buildup. A pressure system operates with lower air compression ratios, thus creating less heat. This results in lower internal temperatures. Further, in a pressure system, air pressure is higher at the pump inlet, located at the beginning of the system. Therefore, cooler, denser air is moved through the pump. This greater density results in both a greater mass of air through the pump and a higher moisture content at the pump. Taken together, this denser, cooler, more moist air, by both cooling and lubricating internal parts of the pump, helps reduce pump wear and extend pump life. Let's take a closer look at both the vacuum and pressure systems. First, the vacuum system. Here is a typical vacuum system in a single-engine aircraft. The engine-mounted air pump draws a constant flow of cabin air through the entire system. Air enters this system through a central air filter. This air is then drawn through the gyro instruments and gauge. Next, a preset vacuum regulating valve located between the instruments and the air pump assures that only the right amount of air is pulled through the instruments, thus protecting the delicate gyros and providing reliable instrument readings. The air pump is at the final point in the vacuum system because, as you'll recall, it is pulling air through the system. Once air is drawn through the air pump, it is dumped overboard. In twin-engine aircraft, the vacuum system is basically the same. However, there are two pumps connected by a manifold with check valves drawing air through the entire system. This provides a backup energy source should one engine or pump fail. Now let's take a closer look at the pressure system. Here is a typical pressure system in a single-engine aircraft. The air pump, also engine-mounted, pushes a continuous flow of air through the entire system. In such a system, necessary air is drawn in by the air pump through an inlet filter. The air pump is located at the front end of the pressure system because it is pushing air through the system. This pressurized air first passes through a pressure regulating valve, which maintains a preset pressure to properly operate and protect the instruments by releasing any excess air pressure. The air at proper pressure then travels through an inline filter which protects the delicate gyros from any contaminants remaining in the system. Finally, the pressurized air is pushed through the gyro instruments and gauge, providing reliable instrumentation for the pilot. The pressure system is basically the same in twin-engine aircraft. Here, two pumps force the air through a manifold with check valves to direct pressure distribution to the airplane's instruments, and again ensures backup energy in case of engine or pump failure. As we've seen in the preceding schematics, both the vacuum and pressure systems are made up of four basic components: dry air pump, regulating valves and gauges, fittings and tubing, and pneumatic filters. Let's examine each component separately. First, let's consider the dry air pump. This remarkable pump truly is the heart of an aircraft's pneumatic system. Like the human heart, the dry air pump is delicate, precise, and yet extremely durable. And also, like the human heart, its internal parts are structured to work in perfect union with each other and with the circulatory system of which it is the main part. This engine-mounted pump generates all the airflow, moving air with a rotor and vanes that roughly resemble a paddle wheel. It either pushes air to create air pressure or pulls air to create a vacuum through the entire pneumatic system. Maximum performance and pump life are achieved through a precision-engineered design, special lightweight materials, and careful construction. For example, the rotor and vanes on airborne dry air pumps are made of a special carbon which is self-lubricating. As the vanes rotate with the rotor, vane tips wear at a precise rate, providing the pump's lubrication. This is why no oil is required. This is also why it's called the dry air pump. Driven by the aircraft engine through a set of gears, the spinning rotor and vanes draw air through the front inlet port, creating vacuum there, and push it out the back outlet port, creating pressure. We compared it earlier to a paddle wheel. Unlike early air pumps, which had short vanes set straight into the rotor, such as shown here, the vanes on an airborne pump are canted or set into the rotor at an angle. This allows for much longer vanes, with a corresponding increase in both efficiency and vane life. However, because the vanes are canted, the rotor can turn in only one direction, clockwise or counterclockwise, depending on the engine's drive pad rotation and pump model. This actually is an advantage, and one of the reasons why Airborne engineered this approach. The unirotational design can increase pump life significantly over that of birotational pumps. Airborne dry air pumps also have a unique patented torsional coupling. Made of flexible urethane, this coupling helps absorb engine vibration, thus increasing pump life. It also protects the engine from damage in the remote possibility of pump seizure by shearing and allowing the drive spline to rotate freely. In addition, airborne dry air pumps have these features: a double offset bore that helps balance internal loads, bearing wear, cooling fins on high-pressure pumps to dispel heat, increasing pump life, and a floating backplate which allows for heat expansion, maintaining pump efficiency and life. A final benefit is the fact that Airborne's dry air pump design features have allowed the development of efficient and long-life pumps for virtually all capacity requirements of today's general aviation aircraft. Next, let's consider another important part of any pneumatic system: the valves and gauges. In order for an aircraft's instrumentation to function accurately, exact vacuum or air pressure must be maintained within the system at all times. Compensation must be made for power surges, engine speed changes, de-ice boot inflation, and the like. This is a job for the pneumatic regulating valve, a precision component which is carefully preset at the factory to match its specific function in the system. There are regulating valves for both vacuum and pressure systems. A vacuum regulating valve is the main valve in a vacuum system. This valve protects the delicate gyro instruments by preventing any excess suction of air through the instruments. Here's how. Because the air pump draws more air than is required to operate the instruments, this preset valve opens a second stream of air to the pump, thus maintaining the proper vacuum level of air being drawn through the gyro instruments. In a pressure system, a pressure regulating valve is used. Since the air pump can push more air into the system than is required, the valve provides pressure relief when needed by opening and thus allowing some air to escape. This reduces any excess pressure into the gyro instruments. Similarly, other valves work in conjunction with various pneumatically powered devices, such as de-ice boots. These valves can be activated by the pilot and used to direct air into the boots, thus inflating the boots and breaking off ice which has formed on the wings or tail, and to remove air from the boots, thus deflating them once ice has been removed. Meanwhile, as these valves are activated in either mode, the pneumatic system remains in balance, the airflow continuing uninterrupted as it performs its other tasks. You'll find special purpose valves such as these in both vacuum and pressure systems, each valve designed to operate under the airflow designed into the particular system. The pilot also has a way of checking on his pneumatic system. He does this through pneumatic gauges on the instrument panel. Just like the valves, two types are basic: vacuum gauge and pressure gauge. Both advise the pilot whether his pneumatic system is maintaining necessary vacuum or pressure. First, the vacuum gauge. Suction measures vacuum in the system by making the indicator needle move. In twin-engine applications, suction also operates a built-in method of alerting the pilot in the event of a malfunction in the system. The force of this suction, or vacuum, not only moves the needle, as you can see at the top of this illustration, it also holds a red ball in a recessed position, as you can see at the bottom. If for some reason vacuum is interrupted, the ball will pop out, indicating that one side of the system is inoperative. In other words, this immediately warns the pilot that half of the airflow has been lost. Meanwhile, proper gyro operation is maintained with the one pump that is functioning properly. In the pressure gauge, air pressure compresses a bellows, which moves the needle to give the pilot a reading on his system's air pressure. In a twin-engine application, in addition to giving a pressure reading by compressing the bellows shown at the top, this same air pressure forces the red ball at the bottom into its recessed position. If air pressure is lost, the red ball pops out to warn the pilot of a malfunction. Next, let's consider some components which are immediately related to the valves and gauges. These are the fittings and tubing through which the air in a pneumatic system flows. Although they are the simplest components in a pneumatic system, the fittings and tubing are just as vital as the rest. Continuing our comparison to the human heart and circulatory system, the tubes and fittings can be thought of as the veins and arteries. Just as the human circulatory system will fail if there is a blockage, so must the pneumatic system have an unrestricted flow in order to maintain the health of the system. Therefore, the pneumatic fittings and tubes, and in particular the fittings, must be carefully tailored to their tasks, providing proper airflow for instruments and other devices. Airborne low-loss fittings, with their wide-open passages, smooth-swept bends, and minimal restrictions, help prevent any loss in the vital flow of air. The freer airflow possible in this modern design becomes even more apparent when it is compared with the older design AN fitting. AN fittings have sharp 90-degree bends that create areas of turbulence and restriction. On the other hand, airborne low-loss fittings allow for a much freer flow at any flow rate. However, these advantages mean little if air hoses are not in proper condition or are not of the proper dimensions. Once correct hoses are installed, they should be checked periodically to detect crimps, cracks, frays, or other potential sources of failures. Now let's move on to another extremely important part of the system: pneumatic filters. It's easy to overlook the fact that the air in a pneumatic system must be clean air. But clean air is essential, and therefore quality air filters, regularly replaced, are also essential. Clean air is needed not only to assure an adequate and unrestricted airflow. The air in a pneumatic system must also be kept clean in order to protect the delicate instruments and the dry air pump itself. To make sure that all of the pneumatic system is kept free of dust, dirt, smoke, and other contamination, several types of filters have been developed by Airborne to provide this essential protection. Let's take a look at several basic types. The inlet vacuum filter is the primary filter for the vacuum system. As the system takes in cabin air, this filter cleanses the air of dust, tobacco smoke, and other contaminants which might endanger the gyro instruments and air pump. Air entering at the regulating valve in a vacuum system must be cleaned by a special foam garter filter, which slips easily over the valves. Filtration in a pressure system obviously is equally important. Here it also begins with an inlet filter, which cleanses the incoming air prior to its entering the air pump. Inline pressure filters are specially mated to the unique characteristics of dry air pumps. Carbon particles may enter the pressure system from the pump as vanes wear down in the process of providing lubrication. So the air is passed through an inline pressure filter before it reaches the delicate flight instruments. This brings us to a final important point. Although they are precision items in themselves, pumps, valves, gauges, fittings, and filters work only as parts of a total system. Pneumatics is more than a collection of parts. It is a complete, integrated system and a vital part of the aircraft itself. A total system. With this important point in mind, pneumatic equipment and components are being designed and applied today with a systems approach. Every part of a pneumatic system should function as balanced portions of a total unit. So every part is designed, manufactured, and mated to function in total harmony. Remember, however, that no matter how advanced designs may become, the efficiency and reliability of any pneumatic system will always be dependent upon regular maintenance and proper mechanical service. And these vital subjects are covered in Part 2 of this film on modern aviation pneumatics. An idea that flies.
Flight, an experience in airborne high-performance products. Freon air conditioning, bleed air valves, fuel pumps, and pneumatic products. Airborne, leading the industry in performance standards for more than 300 products. Based in Elyria, Ohio, we design, manufacture, test, and market products for general aviation aircraft. Our commitment to quality products extends beyond our manufacturing capabilities and is mirrored by the professionals whose skills keep general aviation parts and systems performing every day. Through a constant flow of information and training, our professionals are provided with the necessary experience to deal with pneumatic system field problems. Through the capture of ambient air, we direct its flow for a clean, reliable, and efficient source to operate gyros, inflate door seals, de-ice systems, and operate autopilot systems. Initially, wet pumps were a practical solution, but only for vacuum systems. They were heavy, complex, and consumed excessive amounts of engine oil, not to mention the oil-streaked aircraft belly that resulted. With this, Airborne developed the dry air pump, at work today in virtually every piston-driven aircraft. Our dry air pumps are clean, lightweight, and self-lubricating, eliminating from aircraft the usual oil and dirt contamination inherent in wet pump systems. Our pumps drive the pneumatic system, but every part in the system makes a vital contribution in how long a dry air pump will perform. A well-maintained pneumatic system provides a clean, reliable source of air. Without proper maintenance, the pump becomes the victim of pneumatic system contamination or damage. It's a case of small problems causing major breakdowns. Fortunately, it's easy to identify probable sources of these problems, and it's all in knowing where to look. Consider filters, for instance, the elements that screen impurities from the systems. The central air filter in a vacuum system and the pressure system inline filter safeguard delicate gyro instruments. The vacuum regulator filter and pressure system inlet filter offer similar protection for the dry air pump and its carbon rotor and vanes, which are built to very close tolerances for maximum efficiency. Filters are designed to capture impurities. The more they screen, however, the lower the volume of air that passes through them. As the flow of air becomes restricted, the pump works harder and becomes hotter. This causes increased wear, resulting in a shorter service life. The reduction in the flow of air, as seen in the panel-mounted vacuum or pressure gauges, can be an indication of system restrictions, including clogged filters. Vacuum regulator filters and pressure system inlet filters require replacement every 100 hours or annually, whichever comes first. For central air and inline filters, it's every 500 hours or annually, whichever comes first. During new pump installation, the system should receive all new filters to give the pump a clean, free-flowing system to operate properly. However, filters are only one source of potential trouble for dry air pumps. When hoses are allowed to deteriorate, they become hard, cracked, or brittle. A small piece of hose in this condition can cause big consequences. Broken away from the inner lining, it is ingested into the system, where it can clog or rip filters, lodge in control valves, or even make its way to the pump, where it can't be discharged, jamming the vanes or rotor, causing the pump to fail. Collapsed, kinked, or twisted hoses have the same effect as clogged filters. They restrict airflow and raise pump operating temperatures, virtually guaranteeing increased wear and shortening the pump life. Trouble may also occur when loose fittings create leaks in the system. At any point where airflow leaves the system, pressure or vacuum is lost. In a pressure system, for instance, an air leak will reduce airflow through the gyro. In the cabin, the differential gyro gauge indicates loss of pressure. An immediate remedy is to increase the setting on the regulator so that even with air loss, the pump forces more air through the filter to the gyros. The trouble is, the pump does all the compensating by creating more pressure than the system should need. It overheats, loses efficiency, and fails to reach its potential service life. It's easy to assume early pump failure means a bad pump in a well-maintained system. It's more likely that early pump failure is a symptom of a poorly maintained system. A high-quality hand-built pump performs only as well as the system is maintained. To help ensure a high level of maintenance, we at Airborne have made available a pneumatic system maintenance guide. Designed to be small enough to fit into a toolbox, but big on information, the guide is plastic laminated to resist oil and grease. The format of the maintenance guide enables the professional to use it as a step-by-step checklist, or as a more in-depth source of information. With the help of our guide, a professional can eliminate the causes of early pump failure through effective system maintenance, troubleshooting, and proper pump installation. Performance begins with system maintenance and the avoidance of contamination on the ground as well as in the air. As the engine compartment is cleaned during annual and 100-hour inspections, unprotected pneumatic system components are open to high-pressure cleaning solvents through filters, regulating valves, pump coupling areas, and vacuum system discharge hoses located in the engine compartment. Cleaning fluids can also enter the system through loose fittings or punctured hoses. Replacement of damaged hoses, proper tightening of fittings, and the protection of filters, valves, and coupling areas before engine cleaning prevents contamination that can contribute to pump failure when engines are started after cleaning. When solvent enters the pump, it can mix with the fine lubricating dust of the carbon vanes. This contamination restricts internal movement of the pump vanes and can shear the coupling. A good pump will go bad just as quickly when the accessory drive pad seal leaks, allowing oil to enter the pump. Any evidence of oil around the pad or lower surface of the pump means a bad seal. That calls for replacement of the air pump drive pad seal immediately. Routine periodic maintenance is really nothing more than checking each pneumatic component for blockage, leaks, or damage. That includes fittings inspected for tightness and buildup of foreign matter, and unserviceable fittings that have stripped or burred threads or are twisted, bent, or truncated. These fittings are not airworthy and must be replaced. Whether replacing worn fittings or reinstalling usable ones after cleaning, spray the threads with a silicone lubricant. Do not use Teflon tape or thread lube. After the silicone is dried, install the fittings hand tight. Avoid over-torquing. Tighten a maximum of 1.5 turns with a box wrench. Another way to avoid system trouble is to inspect hoses. Cracked, hard, brittle, oil-soaked, or punctured hoses are considered bad, and they can also cause reduced airflow by kinks, twists, bends, or points of collapse. These conditions mean contamination or reduced airflow and increased wear on the pump, clearly indicating that it's time for a new hose. Lastly, regulators and valves need to be checked for blockage and cleaned of contamination, then properly reset to regulate the correct pressure or vacuum throughout the well-maintained system. System maintenance gets at the causes of early pump failure before they happen. Replace dirty filters, damaged fittings, hoses, and clean the inlet lines to the pump to eliminate carbon debris from the previous pump. Finally, check and clean all regulators and valves in the system. Only after all of these steps have been taken during a scheduled maintenance session can a pneumatic system perform properly. Nevertheless, pumps have been known to fail even in the best maintained pneumatic system. Troubleshoot when a pump has failed soon after installation. When an aircraft has a history of short pump life. When gauges show pressure or vacuum to be above or below proper levels. Or when the gyro performance is erratic and the DI system, door seals, or autopilot systems malfunction. The professional troubleshooter assumes that any pneumatic problem can affect the pump and performs every possible check, from making sure the pump is the right one for the aircraft engine to inspecting all components in operation to identify points of pressure or vacuum loss that may go undetected during routine maintenance. The safest and most accurate way to run a system check is to use the Airborne 343 test kit. The kit is delivered with an instruction manual, which includes a complete troubleshooting guide and step-by-step instructions for checking and setting up a complete system. The 343 test kit provides greater speed, reliability, and safety, rather than makeshift methods or trying to adjust the system with the aircraft engines running. The kit provides a means of adjusting vacuum and pressure systems for both single and twin-engine aircraft. This includes a handheld pressure vacuum gauge to probe the system at various points to verify accurate pressures. It takes a professional to ask the right questions and to adjust the chain of cause and effect that keeps a pneumatic system operating properly and working with the dry air pump, not against it. Even after excellent system maintenance and troubleshooting, dry air pumps have been known to fail. Dropped pumps do fail. Whether or not external damage shows, dropping can cause internal damage, and a new pump can be destined for failure before the aircraft ever leaves the ground. Don't install a dropped pump. Clamping a pump in a vise around the center housing is another very common installation mistake, resulting in premature pump failure. Since only a light vise pressure is needed to crack the carbon rotor, the pump is safest in a vise with protective soft metal or wood jaws clamped around the pump mounting flange. Attention to details such as these go a long way toward making installation time pay off in long pump service life. For example, a careful check that the pump is correct for the aircraft engine includes matching the pump rotation shown on the pump box part number label with the direction of the drive pad rotation. This includes making sure that Airborne's application list and the aircraft manufacturer's parts catalog specify the same pump model for the aircraft. Another often overlooked detail involves the old pad mounting gasket. It is very important to replace the old gasket with a new one, which is included in the pump box. The gasket provides for the accessory drive pad oil hole. It also creates a thermal barrier to protect the pump from engine heat. Pneumatic system care is a cycle of prevention and correction aimed at protecting the dry air pump from system contamination and damage. Preventive maintenance keeps pneumatic components airworthy. Troubleshooting finds the causes of pump failure and corrects system trouble before a new pump is installed. And proper installation safeguards the long life designed into the pump. Quality is in the making of every Airborne dry air pump, but performance is in the hands of the professionals. Any dry air pump is only as trouble-free as the system it's in. The important difference is simply the people who maintain the system. Pneumatics, the use of air, that most available and versatile of all natural resources, can be harnessed safely and reliably by having responsible professionals who maintain clean, unrestricted, properly adjusted pneumatic systems. At Airborne, we are committed to supporting our aviation professionals with vital information and personalized service. Airborne products lead the industry. Discover flight. Fly performance with us.